Will there be any revision sessions? Yes, it's already on the syllabus. I think a week, the Wednesday before the final exam, I will hold a revision session for everyone. Okay, that's during reading week. Yes. So this Wednesday, oh, hello. This Wednesday, we still have class. This is for next week. So we still have tutorial 4. That's on Wednesday. And then next Monday is tutorial 5. And then next Wednesday, there are no classes. So only on 11th of November will there be no classes, okay? So there's still classes on Wednesday. I mean, you don't have to show up, but I highly recommend that you do, okay? All right, guys, it's the last lecture. It'd be nice to see more people today. But okay, it's just the two of y'all. It's okay. Not okay, but I mean, what can I do? All right, so let's go ahead and work on our last topic for the semester. We talked a bit about partial differential equations. Okay. So what is a partial differential equation? An ordinary differential equation is a differential equation where you have ordinary derivatives. For partial differential equations, these are equations that have partial derivatives showing up instead. So our functions now can depend on more than one independent variable. So we've seen some partial derivatives back in 1511, but really this is going to be very similar to that. So here's what we're going to do. Let's just talk about some words that we've developed over the course of the semester, and then see what how they sort of extend to the realm of partial differential equations. So what is a partial differential equation? This is just, we'll call it a PDE, is a differential equation involving a multivariable function now, because it can depend on more than one partial derivatives. So equation involving one or more partial derivatives of an unknown function u, of a function u, that you're going to solve, that our goal is to, of course, solve for, of a function u. So of course, this new function u can depend on 2 variables, can depend on 3 variables, etc. What are words that we have seen throughout this semester? We know how to describe an ordinary differential equation in terms of its order. Order is the highest derivative that shows up. The same for partial differential equations. It's the order of the highest derivative. So the order of a PDE is the order of the highest derivative in the equation. So same definition. Now it's just we have partial derivatives. What other words have we seen throughout the semester? We've seen the word linear. What that means is that my partial derivatives, or in the normal ODE sense, that just means our derivatives show up linearly. So that linear just means it's the highest power of a function and its derivative is the first power. So the differential equation is of the first degree in u and its partial derivatives. Right, linear just means, yeah, first power for the function u and its derivatives. What other words have we seen in class? Okay, we've also seen homogeneous. And we know what homogeneous looks like, right? It's like blah, 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 blah equal to 0. That is to say there are no constant functions that do not depend on u, right? So, so maybe I can say no constant functions. Oh, that's fine. You get what we mean when we say homogeneous. Okay, so what is the general form of, say, a partial differential equation? Let's just go ahead and take a look at an example. The general form of, say, a first order linear might look something like AUX plus BUY plus CU is equal to some function, let's say D. So what do we take note of here? Of course, U is a function of X and Y. It's an unknown function that we're going to solve for. UX is the partial derivative with respect to X. So that's U. How do you want to write this? So maybe let's put this here. U is a function of X. This is just, your partial derivatives. du dx and du dy. A, B, C, D, they can be constants, but they can also be constant functions of x and y. So maybe to note here, in the same way that our coefficients could have been functions, A, B, C, D can be functions of x and y, or constants themselves. Okay. What will make this homogeneous, for example? If D is 0, then the equation would be homogeneous. So if D is equal to 0, then the PDE is homogeneous. All right, very straightforward stuff. It looks a lot like the things we're familiar with. We're just tossing in partial derivatives into the equation. Of course, our goal for today is to solve partial differential equations. Our goal is to solve PDEs. And surprisingly, they won't be too different from our ODEs. Okay, so let's just give a very quick example. So the same Pierre-Simon Laplace did a lot of work in math and physics. So he also came up with the Laplace partial differential equation. So an example of a partial differential equation is the Laplace equation. And what is the Laplace equation? The Laplace equation is the partial differential equation uxx plus uyy is equal to 0. Okay, so this is just an example. I'm just throwing out an example just so that we know what a partial differential equation looks like. Let's try to describe this partial differential equation. First, it's a PDE. It's partial because I have partial derivatives with respect to x and y. The highest derivative showing up in the entire equation is the second derivative. So we say that this is a second order partial differential equation. The coefficients of uxx and uyy are both 1. They're constants, so we can say that this is a linear partial differential equation. And what else can we describe? Oh, it's equal to 0. So this is also homogeneous. Okay. So we've seen an example. Let's put the homogeneous on the next line, maybe. The different. So an example of a partial differential equation, and we're just describing it using the language that we already know. Okay, so there is something interesting about partial differential equations, and I want to take a look at the Laplace equation as our example. So of course our goal by the end of today would be able to solve, and we're going to be solving simpler equations than this, but what does it mean to solve a partial differential equation? It means to find a function u that satisfies the equation, right? For example, if I take the function u of xy is equal to x squared minus y squared. If I compute ux, that's going to be 2x, constant with respect, the y is constant with respect to x, and then of course uxx is going to be equal to 2, and I trust that you guys know how to do this, so I'm gonna skip this and just write uxx is equal to 2. Uyy, on the other hand, is negative 2. Which means if I plug in uxx and uyy, it satisfies the partial differential equation, so we say that this is a solution to the partial differential equation. It just means it's a function that satisfies the partial differential equation. Here's the thing. Let's change our function a bit. Suppose I now look at the function uxy is equal to e to the x cosine y. What is uxx? Oh, it only hits the e to the x term. Cosine y is constant, so it's just going to be e to the x cosine y. What about uyy? In the first derivative with respect to y, cosine becomes negative sine, and the negative sine becomes negative cosine. So this is just going to be minus e to the x cosine y. And if we take a look at this different function, e to the x cosine y, it also satisfies the Laplace equation, the PDE above there, which means this is also a solution to the Laplace equation, the PDE. And we have to be careful now because those two solutions look very different from each other, but they both still work. Okay, so one big difference we have from ordinary differential equations is that now our solutions can look completely different, but all still work. In the ODE case, in the ordinary, what we've been doing for the first 4 weeks, it's very clear that, okay, if it's a separable, all the solutions look alike because of the sort of arbitrary constant, right? We just changed the arbitrary constant, but all of those solutions look the same. However, in this case, we have two completely different looking functions that both solve the PDE. So that's something that we want to be careful about. Okay, so one thing I should say is which solution do we pick? It depends, of course, on the initial and boundary conditions that you are given to solve the PDE. So in this case, because there are no initial conditions, both of these are fine, but if we're given initial conditions, we will need to determine which one is the appropriate solution. So let's just state one theorem, and this is going to parallel something we've also seen before. So this is Theorem 1 for today. We've heard about the superposition theorem all the way back in week 2. What does the superposition theorem say? Superposition theorem just says if I have two solutions to a homogeneous differential equation, their sum is also a solution. And that extends to PDEs as well. So let's say that I have two solutions, U1 and U2. Solutions to a partial differential equation. Then, not any partial differential equation, let's emphasize to a homogeneous partial differential equation. Then any combination of these two solutions will also be a solution, okay? Then let's say U, which is C1, U1 plus C2, U2, is also a solution. To the homogeneous PDE, right? Is also a solution for all C1, C2 in the real numbers. So maybe one thing to note is that this is not necessarily a similar case of, oh, C1 and C2 are the arbitrary constants we need to solve for. Because for instance, in the Laplace, in this sort of Laplace example that we saw earlier, the Laplace equation, right? It's uxx plus uyy is equal to 0. We know that x squared minus y squared is a solution. Okay, so we know that x squared minus y squared is a solution. So any scalar multiple of x squared minus y squared is a solution. So for example, 20 x squared minus y squared. I also know that e to the x cosine y is a solution. So if I do minus 10 e to the x cosine y, then this function, a combination of those two solutions, is also going to be a solution by the superposition principle. Okay, so what the superposition principle just says is that if I have a lot of different solutions, if I add all of them up, combine all of them up, that's still going to be a solution. All right, any questions about the basics of partial differential equations and the ideas of solving, or not necessarily solving, but using a solution or checking that something is a solution and combining solutions to create more solutions from that? That should be fairly straightforward, nothing too crazy just yet. So now we start solving our PDEs, and it's getting quite dark on my side. It's okay, I don't think I need to turn on the lights yet. All right, so let's start solving PDEs. There are infinite solutions. In most cases, yes, there are infinitely many solutions, and the tricky part is most of them probably don't look alike, look like each other, right? So for example, these two are just two. If I, for example, gave you sine x hyperbolic cosine y, that would also solve the Laplace equation. So there are really infinitely many solutions, yes. Okay, what method are we going to use to solve partial differential equations? We're going back to where we started. The separation of variables. Slightly different from the separation of variables that we did, but the idea is the same. When you have a partial differential equation, you have a bunch of x's, you have a bunch of y's, so try to move all of your x's and y's to each side of the equation and then solve both directly. But there is a minor tweak that we're going to have to do. So for this, rather than guiding you through an example, I'm going to give you the steps, and then we'll use the steps to see how it relates to a more general example. So this is a 4-step process. So first step, you're going to assume the form of the solution that is separable into its x and y variables. Suppose that a solution u is equal to x times is a function of x, y a function of y exists. So you don't know if this is true, but you're just assuming that a solution of the form a function of x times a function of y exists. If you want to call this f of x and g of y, that's fine too. I'm just going to use big X and big Y to emphasize that I'm dealing with x's for one function and y's for the other function. Next, replace your PDE or rewrite the partial differential equation in terms of your new solution, your assumed solution. Rewrite the PDE in terms of x and y. Or let's say in terms of u is equal to x, y. What does this mean? What does it mean to rewrite everything in terms of ux, y? Your partial differential equation will contain ux. Everything with respect to y is constant when I differentiate with respect to x. So this is just going to be x prime y, right? Where x is a function of x, so I can use x prime. If I have uy, that's going to be xy prime. If I have a second derivative, so on and so forth. So I can replace everything. I can completely replace all the u's with expressions in big X and big Y. Separate all the terms involving X. So all the terms moving all of the X's to one side and all of the Y's to one side. Involving X from those involving y. I'm going to put ... here, meaning there's something we're going to have to do. And I'm not going to say what that is yet. We'll say it when we do an example. And the fourth, once we've separated all the variables, we can ready to solve two ODEs, two ordinary differential equations. One in x and one in y. Okay, because the left side is all x and the right side is all y. Okay, so here's the question. What is the ... How do I jump from an expression where everything here is in x equal to everything here is in y, and these are all functions of x, these are all functions of y. How do I move from that to two separate ordinary differential equations? This equality means that no matter what x I plug in, it's going to be equal to this expression no matter what y I plug in. So what that means is both sides have to be equal to the same value. They can't be equal to a changing function. They have to be equal to a constant. Okay, so what the missing part here is that we need to equate both sides to a constant. Let's put that here. Equate this to k, to some constant k. Right, and then we're ready to solve. So I'll do an example. Let's highlight this. This is it. This is the only method you're gonna know how you're gonna use. So everything that we're gonna do today is sort of based on this. Okay, the separation of variables for partial differential equations. So example. Let's take a look at this partial differential equation x u x plus u, equal to u plus y u y with initial conditions u1 1 is equal to 2 and u1 2 is equal to 8. Okay, we're going to solve this partial differential equation. We're going to follow our steps for the separation of variables. First, I need to find a way to actually separate the variables, change everything into x and y. So suppose, first step, suppose that your solution u is a separable function x of x times y of y. Okay? We're going to rewrite the partial differential equation now. The PDE becomes, well, what does it become? X stays there. Ux is the derivative with respect to x. So this just becomes x prime y is equal to u is just xy. So let's say big X, big Y, plus y times what is uy, but the derivative with respect to y. So xy prime. Okay. So we've just substituted using our trial solution. Third step. We have our expression all in x and all in y. So our job now is to separate the variables. Okay, move all of the x's, including the big X prime, to one side, move all of the y's to the other. So we separate the variables. Let's do this carefully. On the left, we have x prime. On the right, I can factor out a big X. So I'm going to try to write this properly. Small x over big X, x prime, is equal to, on the right side, I have y. I'm going to divide by y, so I'm left with a 1 plus y over big Y, y prime. Yes. The 1 you can put on either side of the equation. So what I'm going to do is I'm going to move 1 to the other side, to the left side of the equation. So I'm going to do x prime 1 minus 1 is equal to y big Y, y. Okay, so we've literally just used algebra to move all the x's to one side and all of the y's to the other side. Now, the left side is completely equal to the right side, so they both have to be equal to some constant value. So what we're going to do now is we're going to then take this, both sides of the equation have to be equal to the same constant. Let's call that constant k. What that means is we have one differential equation in x and another differential equation in y. Both ordinary, no longer partial. Okay, so let's go ahead and solve the two ODEs. The 1 can be kept on the right. Yes, you can keep the 1 wherever you want because it doesn't depend on either x or y. So let's just solve the two ODEs then. My first ODE is in x. X over big X, x prime minus 1 is equal to k. How do we solve this differential equation? X prime is just d big X over d small x minus 1 is equal to k. Or let's say is equal to k plus 1. Oh, very nice. This is a separable differential equation. Right, so let's separate the variables. 1 over x d big X is equal to k plus 1 times 1 over small x d small x. I'm ready to integrate both sides. Then my function becomes ln of big X is equal to ln of small x times k plus 1. Don't forget your plus z. I can exponentiate both sides to make it nicer. So what is my function big X of x? Big X of x is just some constant a, no more e because the x is inside a ln as well, x to the power of k plus 1, where a is a real number. So what we've done is we've solved the left-hand differential equation in big X and small x. We're now going to do the same for the right-hand side for y. This is going to be small y over big Y. Y prime is equal to k. Also a separable differential equation because this is just the derivative of big Y with respect to small y. We already know what this is. 1 over big Y d big Y is equal to k over small y d small y. This is just y of y. Well, it's a ln on both sides and then exponentiate. It's just going to be by to the k for some real number b. So what is our solution? Oh, this is great because we assume that the solution was of the form big X times big Y. We've solved for big X. We've also solved for big Y. So the solution, just multiply the two. So our solution, by a separation of variables, is u of xy, the product of big X and big Y. Ax to the k plus 1 times by to the k, I can combine my a times b into a single constant. So let's just call it c, x to the k plus 1, y to the k. And let's highlight this. This is our general solution to the partial differential equation. So it looks a little bit different from what we would normally do, but it's actually fairly straightforward, right? Find a way to rewrite everything as a separable variables. What's the difference between lowercase and uppercase? The lowercase is the independent variable. The uppercase denotes a function of that independent variable. Nope. I am assuming that the solution is a product of big X and big Y. So if I find another one using a different method, then the superposition principle tells me that I can add them up. But the important thing here is in order to be able to separate your variables nicely, you have to assume that it's a product. Okay? Yeah. It's easier to separate the variables if we assume that it's a product. Of course, you can assume that it's a sum, but you might not necessarily get a nice, clean answer with that. Also, this is just one method of solving PDEs. This is the only method we do in this class, by the way. There are other methods that might get you completely different looking answers. But just for this is the only method we're going to work with. Okay. Yeah, so for the two ODEs, we multiply because that's what our assumption was. Over here, let's highlight. But if I have different solutions, then I can add them by the principle of superposition. The solution to PDEs are families of solutions, sort of. Yes, so your ODE has a family of solutions, but there's not only that family, there are many different families. For example, the x squared minus y squared and the e to the x cosine y are their own families, so you can combine. Yes, so this is just one of the solutions, or just one family of solutions. Yes, there might be others that we don't know by this method. Yeah, okay. So if you want to do superposition, you need to find another one. But we only care about finding this one for this class, don't worry. Okay, question, are we done? Are we done with this problem? Done, yes, no? Yes, Donglin. We have initial conditions, so we need to find the arbitrary constants. Okay, so we have, in this case, we have a special step 5 because we have initial conditions in U11 and U12, then we need to substitute those. So find the particular solution. So I know that U11 is equal to 2, so I'm just going to plug in x is 1 and y is 1, so that's equal to c, so that's just equal to 2. And U12, I already know that c is 2, so I'm just going to plug in 2. 1 to the k plus 1 is just 1. I am left with y to the k, so 2 to the k is equal to 8. So k has to be equal to 2 in this case. So what is the actual solution by the initial conditions? My actual solution, uxy, I have to replace my c and k correspondingly. It's going to be 2x to the 3y squared. Can the initial condition given be a partial derivative? Yes. In the same way that some of your initial conditions were velocity and not position, right? In this case, and I gave you the, not really initial, I guess these are technically more like boundary conditions, but the initial conditions can be given as partial derivatives too. Okay, sorry. There you go. Any questions about the separation of variables? You'll get a lot of practice for this for the tutorial. So one thing I would recommend is right after this class, just give. We're gonna do another one halfway through today, but just try your hand at doing some of them, and then I'll give you guys more practice during the tutorial next week and the additional exercises. Okay. Variable for you are both small x and small y. Yes, everything is in terms of small x and small y. So what you're doing is you're assuming that I can separate small u into a product of a function of just x and a function of just y. Any questions? No. Okay, so this is our main method. This is the only method for PDE. So we're essentially done for today. So for the rest of today, what we're going to do is we're going to just focus very specifically on two PDEs that show up a lot in physics, in science, in math. Okay? So the first PDE I want to talk about is the heat equation. Oops, sorry. The heat equation, which models the dispersion of heat in an object. So why is the heat equation going to be a PDE? Of course, as time passes, the heat temperature is going to change. But if I have an object that has more than one dimension, then the temperatures at different positions of that object is going to change as well. So I have to have variables of time and position. So what are we going to consider for the heat equation? We're going to start with some assumptions, and we're going to derive the heat equation. Okay. So consider. We will consider. The temperature of a uniform rod. So let's just give it 1 degree of a uniform rod. Under the following assumptions. Where first assumption on this uniform rod, the rod is of length L. Second assumption, the temperature at every slice, at every cross-section of the rod is constant. So we don't care about the vertical, we only care about the horizontal temperatures. At every cross-section is constant. And last assumption, the rod is insulated at its ends. Okay, so heat only travels horizontally. The ends. Okay, so what does this situation look like? So suppose I have maybe let's draw the rod. Something that looks like this. Oops. Yeah, so this is my rod. What am I gonna do to this rod? I'm assuming that at every cross section, say the heat is gonna be constant, so I don't really care about the vertical direction. I only care about the heat in the x direction. It might be different at every cross section, and how the heat might disperse over time. So what are we gonna do? We're gonna start by the rod is like super cool at the two ends, so it's insulated at the two ends. And to start, I'm gonna put maybe candles under the rod. So it's a metal rod. I'm gonna start by lighting candles beneath the rod. So it starts to get really hot at certain points. And then when I take the candles out, the heat starts to disperse to the other parts of the rod. Okay, so I take the candles out, the heat is there. Because heat will transfer naturally, it's going to move slowly to the other parts of the rod. So the question is, how do we model the temperature of a rod at a given time and at a given position? So if I take a snapshot of this right when I remove the candles, what it might look like is at a fixed time, say time 0, this is my x position and this is my temperature T. What might it look like? Oh, it's super hot here, and it's sort of not as hot in the other. So maybe it looks like sort of like almost a sinusoidal curve, but not exactly. It might look something like that. So this is just a sketch, by the way. Of course, if I put the candles in a different place, I would have a different initial graph, but I'm just using this as an example. Now, the question is, what can we use to approximate the change in temperature? At which part will my temperature move away the fastest? At which parts will the heat disperse more slowly? Well, of course, if I am at a point where I just remove the candle, that's going to be really, really, really hot there. Which means that the rate of change at that point is going to be the fastest. That's the point at which my heat is going to try to disperse the most. Okay? So what that tells me is, depending on where I have, so the concavity of my graph, I have a sort of big pull. As time passes, I have a big pull to return to equilibrium, to sort of even out my temperatures. I have slightly less of a pull on the sides, but the biggest pull, the biggest sort of desire to return to a colder temperature is where the heat is the highest. So what can we say about this? We can say that the temperature's rate of change is proportional to the concavity of my graph, to how steep my graph is. It's proportional to the concavity measured by the second derivative with respect to position. Okay, so we have two derivatives here. With respect to time and with respect to position, my second derivative with respect to position tells me how steep my graph is, or the concavity of my graph. My rate of change of temperature tells me how fast it cools down. So what does this tell me about the heat equation? I can write the heat equation in the form UT is equal to K U X X. Okay. Now, is K positive or is K negative? Well, the rate of change is positive if the concavity is positive as well. So K has to be a positive constant. So what is the actual heat equation? We can write it as UT equals KUXX, but I'm going to rewrite it to emphasize that K has to be positive. The heat equation I'm going to write as, let's write heat equation. UT is equal to C squared UXX. This will emphasize that your proportionality constant is positive. Square number. It's a square value. Okay, so let's box this in. This is the heat equation. We're not going to derive what C is in terms of the other variables. All we need to know is that the rate of change of the temperature is proportional to the concavity of my graph. Can you explain the concavity part again? Yeah, sure. So UXX, the second derivative, measures essentially like the bends on my graph, right? So for example, if you're investigating, oh, is this a maximum or is this a minimum, you would be looking at the second derivative. Am I facing up, or am I opening up? Am I opening down? Now, my pull to temperature goes down when I have peaks. My pull to temperature goes up when I have valleys. So when I have positive UXX, the rate of change positive, that means it's a minimum, right? My rate of change has to be positive as well, moving up. If I have maximum, then my temperature has to be going down. Okay. So the proportionality constant is positive. Why is it C squared? To emphasize that K is positive. Okay. U here is temperature. Yes, U is the function that measures temperature. Okay, maybe let's put that. That's important. U Tx is the temperature at position x at time t. Okay, good. Any questions? Now, this is not enough. If I need a specific solution, I need the initial conditions, I need boundary conditions. Now let's use our intuition here. How many derivatives show up? This is a second order differential. No, the graph is actually three-dimensional. That's why this is a snapshot at time t equals 0, right? As time passes, there's going to be a change in the graph as well. Okay, so I have first derivative with respect to time and two derivatives, second order derivatives with respect to position. So I need three initial conditions for three conditions to solve for a particular solution. So let's now take a look at the conditions for the heat equation. The first condition is from the assumption, right? That the rod is insulated at both ends. So at any time, the temperature at both ends of the rod has to be constant. That constant is going to be, we'll set it to 0. Okay, so our boundaries, these are the boundary conditions. At the ends of the rod, at any time, ut0 and utl, which is the length of the rod, they have to be 0. Okay. Second, so we have two conditions, and these are my x conditions. This is changing position. So I've dealt with a uxx. I now need a condition with respect to time. Well, what is going to tell me what the condition with respect to time is? Well, the nature, how my heat will change, will depend on how many candles I put. If I put 3 candles, then I'm going to have 3 peaks, and I have 3 different parts. If I put 4 candles, I'm going to have 4 peaks. So in essence, one thing that I have to take care of is at time 0, what is the distribution of heat on the rod before, like right as I take the candles out. So let's add now our initial condition, because this is the condition at time 0. At time 0, there will be a distribution of temperatures that depend on its position x. So let's give that a function. Let's call it that function f of x. So u0x. I don't know what f of x is. It's just a function that tells me how the temperature is distributed at time 0. So I have 3 conditions, 2 for position, 1 for time, and that matches up to our second order differential equation. Okay? Any questions about the heat equation and the conditions for the heat equation? Explain initial conditions again. So what my function u is going to look like will depend on how many candles I have, right? So how many candles I have is essentially saying what is the distribution of heat along my rod. So I'm assuming that the distribution of heat is a function of x, function of the position. So my initial condition is that at time 0, the distribution of heat is given by a function f of x. Can you explain uxx? Uxx is a measure of concavity. So think of second derivative test. So for example, if I have a maxima, then my uxx will be negative, right? Which means there will be a pull down. The temperature is likely to go down. And then if my uxx is positive, then I have a minimum. So my temperatures will be pulling up, will be going up, will be increasing. Okay, heat equation. How to find out how many conditions? Look at your differential equation. Look at how many derivatives you're taking. Okay, so you're taking 2 derivatives with respect to x, 1 derivative with respect to t. So 2 conditions with respect to x and 1 condition with respect to t. Why is k always positive? Because if I have a peak, that means I have a maximum, uxx is negative, my temperature will tend to go down, will want to go down. So the rate of change of temperature is has a direct proportion, positive correlation to, or positive proportionality to the concavity of your graph. Why is the boundary 0? Because of our assumption that the rod is insulated at the ends. Okay? Okay, good. Any other questions? Now is the time to ask questions about the sort of intuition of the heat equation. Boundary means both ends, yes. The boundary, like the end, the starting point and the ending point. You know what we're gonna do? Oh, so the rod will never heat to a constant temperature. Well, we'll see what the solution looks like. You know, that's what we're gonna do next, right? This is a PDE. We're gonna solve the PDE. So we'll see what the solution looks like. We're gonna see what is the overall general trend of the solution. Isn't it negative UT? Why would it be negative UT? Right, if I have a peak, that means my UXX is negative. My rate of change of temperature is also negative. So the signs of UT and UXX will be the same. Okay, let's solve the heat equation. What is the only way we know how to solve differential equations? Separation of variables. Okay, so let's go ahead and solve the heat equation by a separation of variables. By a separation of variables. Okay, first step. Assume your solution. Suppose that your solution is a product of, in this case, our variables are x and t, so I'm going to use x times t. Suppose that u, tx, is equal to big X times, a big X a function of x and big T a function of t. What does the differential equation become? The PDE becomes, replace everything, ut is just t prime, or sorry, xt prime is equal to c squared, uxx is going to be x prime prime t. And now we separate the variables. Move all the x's to one side, move all the t's to the other. 1 over t, t prime is equal to, where do we want to leave the c? Let's leave the c with the t. So let's do a 1 over c squared, because it's first order. The reason I'm avoiding the c with the x is because the x is going to end up being a second order because of the second order. Once we've separated the variables, as t and x change, they both have to be equal, so we set both sides equal to the same constant k. And now we are ready to solve the two ODEs. The left side is the easy ODE. It's just a first order, right? I just have a 1 over c squared times 1 over big T, d big T over d small t is equal to k. That's just your exponential curve. Okay, so I'll leave you guys to do this. I think this is manageable. T of t is equal to some constant, let's call it d so that we're not repeating the c, e to the c squared kt. Okay, so move your k times c squared, ln of both sides, or sorry, ln of the left side, and then raise exponentiate both sides. Okay, so this is your t. You also have to solve the ODE in x. So let's go ahead and do that. Second order, 1 over big X, d squared x over dx squared is equal to k. Or if I multiply throughout by k, I have x prime prime minus kx is equal to 0. Now what are the solutions of the second order differential equation? We know how to solve this. You just check your characteristic equation. That's just going to be lambda squared minus k is equal to 0. And depending on the value of k, you have either exponential, combination, or trigonometric. Okay, when we write our answers, do we have to write tt? You can just write big T is equal to that. Yeah, I'm just writing this to emphasize for now, but you're free to write big T is equal to that. Okay. Now, we have three possibilities here, right? E plus E plus xe, and sine plus cosine. Which one do you think it's going to be for this one? yeah, it doesn't make sense that the distribution of temperature will follow an exponential curve as the position. It doesn't. What really would make the best sense here is when your distribution of temperature follows a trigonometric function, right? Because your endpoints have to be fixed at zero. There is no way that an exponential curve will send you back to zero at the two endpoints. So the only way from the physical situation, sine plus cosine has to be the solution, which means that k has to be negative. So from our initial conditions, from the boundary conditions, k has to be less than 0. Which means our solution is a trigonometric. X is equal to a cosine square root of negative kx plus b sine square root of negative kx. Right, square root of k. Since k is negative, I put a negative to make it positive. K must be greater than lambda squared. No, I just need lambda squared equal to k to give me complex solutions, right? So the only way this is going to happen is when k is less than 0. So we're pretty much done. We're ready to combine our two solutions. Okay? So t times x. So what is our solution? U of xt, or U of tx, is equal to, ooh, this is a bit long. I'll just absorb all of the constants into the d into the a and the b. So this is going to be an e to the c squared kt times, let's call it alpha, cosine square root of minus kx plus beta sine square root of minus kx. Oops, there you go. And this is the solution to the heat equation. Oh, are we done? No, because we have initial conditions. We have 3 initial conditions that we need to plug in to figure out the values of the unknowns k, alpha, and beta. Oh, and that makes sense. We have 3 unknowns. We have 3 initial conditions. Okay, so let's copy this onto the next page, and let's just erase. I'm going to erase the working for the separation of variables, okay? All right. So this is our solution, and we plug in our initial conditions. So let's move that up there. What are the initial conditions? Okay, at the endpoints, I need them to be equal to 0. So when x is 0, so let's use the conditions now. First condition is ut0 is equal to 0. So let's plug that in. T stays there. So this is going to be e to the c squared k. Alpha cosine 0 is alpha. Plus beta sine 0 is 0. So let's actually just move that. Here we go. So alpha e to the c squared k is equal to 0. Oh, automatic, very nice. Alpha has to be 0. Oh, I forgot the t. Yes, the t should be still there. T, there. Because e to the t will never be equal to 0. So from our first initial condition, alpha is equal to 0. Or sorry, from our first boundary condition. Next boundary condition, UTL. Let's plug that in. I already know alpha is 0, so e to the c squared k t times beta sine square root of minus k l is equal to 0. e to the t will never be 0, so automatically beta sine square root of minus KL is equal to 0. Now, what does that tell me? You're like, oh, beta 0. But beta cannot be 0, because if beta 0, then the entire expression is 0. So the second expression actually tells me something about k. Right? This tells me that since, let's put this here, since beta cannot be 0, then square root of minus KL has to be a multiple of pi. Has to be a multiple of pi, yes. So square root of minus KL has to be equal to some n times pi, where n can be anything at this point, any whole number. So square root of minus k has to be equal to n pi over L for n in the natural numbers. Okay. Not integers, because actually integers technically can, huh? Yeah, we can put integers. That's fine. Yeah, that's fine. That's okay. All right. So what does this tell me about k? Ooh, k is a bit of a messy expression. K is equal to negative n squared pi squared all over L squared. Where n, I'm allowed to use all of the n's, right? N0, N1, N2, N3, N4, so on and so forth. So what is our solution so far? Let's just combine everything. UTX is equal to, ooh, my k I have to replace by that long thing. My beta is going to be there as well. So let's put that beta e to the c squared, and then k is that long thing. So minus c squared, n squared, pi squared, all over L squared. Yikes. Oh, there's still a t as well, right? Pi squared t all over L squared. Sine n pi over L x. Now here's the thing. Depending on what n is, your beta might change, right? Because your beta, the only thing you know about beta is not 0, and beta might be a different value for every n in the integers. So, is there a minus for e? Yes, because the k has a minus sign here. Sorry, the k has a minus sign. So just carry that. So beta, we'll call it beta n, where beta n changes the value depending on what n of the integers you plug in. Okay? Now, how do you find beta n? That's where your f of x comes in. If you plug in t equals 0, that automatically tells you what beta n's value has to be. Okay? So this is our solution to the heat equation. From this point onwards, you are free to quote this. Okay? So no need to derive everything from scratch, and put a footnote here. Beta n is determined using your other initial condition, u0x, your only initial condition, equals f of x. Okay? So I'm just gonna go out on a limb here. I'll do one example, and then we'll take a break after the example, just so that this is still slightly fresh in our minds. The example is really short, so not to worry. So I want to, for this example, just to show you how to use the solution, I want to solve ut is equal to 2uxx, where x only goes from 0 to 3, and you have initial conditions. ut0 is equal to ut3 is 0. That's the endpoints. The length of the bar is 3, and at the endpoint is 0. And the initial condition is u0x has a distribution of temperatures 5 sine 4 pi x. So 5 sine 4 pi x gives you the initial distribution of temperature at time 0, right when you remove the candles. First thing you notice, oh, this looks a lot like a heat equation. This is just a heat equation. Oh, wow, the thunder is crazy. This is the heat equation. What are the constants? C squared is equal to 2. Right? I'm just mapping C squared to 2. The moment we have that, we're actually ready. Oh, what else do we know? The length of the wire is 3. The length of the rod is 3. And your initial condition, F, is equal to 5 sine 4 pi x. Which means we already have the solution. The solution to this heat equation in this specific form and under these conditions is U is equal to beta n, where beta n is to be determined. E to the minus C squared is minus 2 n squared pi squared t divided by 3 squared 9. Sine n pi over 3, your length is 3, times x. How do I find beta n? I use my initial conditions. At t equals 0, u is equal to 5 sine 4 pi x. So let's just equate that. u0x is equal to beta n. E to the 0 disappears. I have sine n pi over 3x is equal to 5 sine 4 pi x. Ooh, this already tells you what n has to be and what beta n has to be. So n is equal to, I need n pi over 3 to be equal to 4 pi, so n has to be equal to 12. I'm sorry. And what is beta 12? It's just 5. So we're ready to now rewrite our solution. This is going to be 5e to the minus 2n squared is 12 squared. So that's 144. Let's add a multiply a 144 there. Pi squared t over 9 sine n is 12. So this becomes a 4 pi. And that's it. That's your solution. So this is your final solution. This tells you the distribution of heat on your rod at any given time at any given position. Awesome. It's 3:05. Let's take a 5-minute break and absorb this. Very new, just because we're realizing once we have the solution, it's all a matter of algebra, right? So I'll turn on the lights after I answer this question. Okay. Can you explain why we use complex numbers when looking at lambda squared minus k is equal to 0? So we don't know what the original value of k is, right? The issue is, depending on the value of k, I either have exponentials or a trigonometric. What function will allow me to have a distribution of heats that have zeros at the endpoint? It's only the trigonometric, because the exponentials are all going up or going down, right? So in order to have the same value at 2 endpoints, it has to be trigonometric, so k has to be negative. Okay, next. Why is beta n 5? We're just comparing coefficients. So by comparing the insides, I know that, by comparing the insides, n has to be equal to 12, which means beta n is going to be, beta n is beta 12, and beta 12 has to be equal to the coefficient 5. Can't n pi over 3 be any form of 4 pi? Yeah, so it technically, this sort of, this here, you can use any form, but this is the cleanest form, yeah. Good. Okay, let me turn on my lights. I'll be right back. what is n? It is just the index of whichever period of you're taking, because you need square root of minus KL to be some multiple of pi. So n is just to denote any multiple of pi, which means you have possibly many different solutions here. Yeah, so in essence, if you look at this, your arbitrary constants are k, alpha, and beta. And then what you realize is you can replace it by beta n and n as a unit that comes together here. Okay, it's 3:10. Don't worry, the last part of class is not gonna be, it's not gonna be as intense as the heat equation. I think it's slightly, we'll see how far we get. Okay, so we do one more thing, just one last thing for today, okay? Last thing for today, we've talked about the heat equation. We're now going to talk about the wave equation. Good news is that we're not gonna solve the wave equation, okay? You'll be given the solution to the wave equation. We're not gonna solve it. What are the assumptions for the wave equation? I wanna model the motion of a wave or a piece of string, right? So consider a piece of string. What are the assumptions that we want to make on our piece of string? The mass per unit length of the string is constant. Mu is the mass per unit length is constant. What other assumptions do we want to make? The string is super flexible. The string does not resist bending. So it'll free to move up and down. And the string is fastened at its two endpoints. And let's fix what the endpoints are. Let's make it not arbitrary. The string is fixed at x equals 0 and x equals pi. What other assumptions do you want to make? And the tension is large enough so that all other forces are negligible. So gravity doesn't act on, or gravity is negligible on the spring. The tension is so strong that gravity doesn't matter, and like air resistance doesn't matter. So tension is large enough such that all other forces are negligible. Okay, so what does this situation look like? So maybe there's two people here. This is Jeremiah, and then this is Weta. And then they're holding a piece of string. Okay, so maybe let's draw the piece of, they're sort of holding a piece of string like this, and Jeremiah wants to catch Weta's attention, so he flicks the string, so it makes an initial shape. So the string is flicked, so maybe there's an initial bend here, and then of course after the flick, that's the initial flick, the string is gonna, that wave is gonna move towards the other side. Okay. Do we want to do this the fun way or the hard way? Let's do both because we have time today. Okay, let's model the wave equation. Let's take a look at that wave. So let's say at snapshot, at time 0, what is happening on our string? Well, at time 0, maybe a section of my string will have a curve that looks like this, or maybe let's say this is the equilibrium. Let's draw the equilibrium in the sort of taut string here. Sorry, use the blue line. And then there's this initial shape that is made. what is going to be the motion of my string like? Well, again, the highest parts will be pulled closer, will be pulled the most back to equilibrium. There's going to be the strongest pull back down here. Well, of course, as the string moves forward, right? The string moves on. The strongest pull happens where the peaks are, and then we have slightly weaker pulls on the side. So easy intuition for the wave equation is that now, what are the sort of, let's move this. What are the variables at play here? Of course, we care about time. We care about position. Let's just make sure x equals 0 and x equals pi. The ends of the string. What are the sort of derivatives that are being related to here? The force that pulls the string down is proportional to its concavity. Yes? The force that tries to return the string to equilibrium is proportional to concavity. So let's write that here. Force is proportional to concavity. We know what that is, uxx, where u denotes the position of the string at a given time. What is force? Force is just mass times acceleration. So mass times acceleration is the second derivative with respect to time, utt. Is equal to, or sorry, is proportional to uxx. So what is our wave equation? The wave equation is ytt, oh sorry, let's use u because we've used u all of today. Utt is equal to kuxx, where what does u represent? U tx is the vertical position of the string. Okay? Vertical position of string at a position x time t. Okay. Any questions? Should I challenge y'all? I think cannot. Yeah. Oh, K positive again. We don't know yet, but we're now gonna show that K is positive. Right. Well, if it's a minimum, then it's gonna return. Yeah, so K is positive, yes. So maybe we can write that there. K has to be positive by the same reason earlier, so this is gonna be C squared. Where the proportionality constant is positive. Let's figure out what C squared is, okay? So, for the remainder of today, we're not gonna solve this equation because that's gonna be part of the tutorial. We're going to, oh man, I'm laughing as if it's a mean thing. No, the solution is already gonna be given to you guys, and all you have to do is check that the solution satisfies this, okay? So, we're gonna derive what C squared is. We're gonna figure out what C squared really is, what it represents. Okay, so let's derive the wave equation. To derive the wave equation, I'm going to consider an infinitesimally small piece of string. That is to say, a really, really, really tiny bit of the string. It's so tiny that it's almost approximated. Even if there's like a slight curve there, it's almost approximated by a line. So let's just take a look at it. Let's draw our axes. The tiny piece of a string, it's like at a snapshot in time. Maybe this is the string at that time. What are the forces acting on that string? There is a tension force that's pulling it that way. There's also a tension force maybe pulling it this way. Let's just resolve the force. Let's draw it a little bit more nicely. there you go. There's a tension force this way and the tension force that way. Let's denote some variables here. This section of string that we're looking at goes from x to x plus dx because it's so tiny, dx almost goes to 0. And the angle it makes, or the angle this makes is, let's say, oops, sorry. Let's draw these lines here. Let's suppose that this is an angle theta, and this is an angle theta plus d theta. With the blue arrows are the tension forces that pull on the string. It's so tight. Right? Okay, so we assume that no other forces are in action, so the string is also fixed, so it's not moving left and right. It's only moving up and down. So the only thing we really care about are the vertical components of the force. Okay, so it suffices to consider the vertical components of the force acting on the string of the forces. So what does that tell me? I'm just going to take the vertical components of those two tensions. The top one is going to be T. Vertical component will be sine. Okay, sine of theta plus d theta. Downward will be in the opposite direction. So minus T, that's also going to be sine theta, vertical component. Okay, so this is the force acting on the string at that moment in time. Because we're looking at such a tiny piece, theta is going to be really, really, really small. So since theta is really, really small, then sine theta, we've seen this in the pendulum before, is approximated by theta, which means our equation just becomes f theta plus d, t theta d. Oh, let's write that on the next line. F is equal to t theta plus d theta minus t theta, which leaves me with t times d theta. Okay, so the total forces acting on the string is just t d theta. By Newton's second law, this is equal to mass times acceleration. So by Newton's second law, mass times acceleration is the summation of forces. What is the mass? Oh, I assume that the mass per unit length is mu. So I have mu. What is the unit length I'm looking at here? dx. dx plus dx. So mu times dx, that's my mass. My acceleration is the second time derivative, so let's call that utt. So this is my mass. Acceleration is utt, is equal to the summation of the forces, that's t d theta. So what's going to happen? utt is equal to t over mu d theta over dx. And we're very close now because we have the utt, we have the c squared. I just need to figure out what d theta over dx is. Okay, so how do we replace d theta over dx? I need to replace theta with everything in terms of u and x, right? So we have, well, what is tangent theta but the slopes of the lines? So that's your du dx. This is du, oops, over dx. Why is m mu dx? This is mass per unit length and the length. Mass per unit length times length gives me mass. Right? Tangent theta is du dx, or partial of u with respect to x. So I just need to replace d theta dx. Well, what's it going to be? Let's see. I know it's going to end up being uxx, so let's just figure that out. Uxx is d squared u over dx squared is equal to ddx of du over dx, that's tangent theta, so that I can replace it with theta. And this is just 1 over cosine squared theta d theta dx. sorry. Almost there, because there's a cosine theta if I want to replace this with uxx. But very nice, theta is very small, right? So since theta is approximately 0, cosine squared theta is approximately 1. Very nice. So uxx is approximately theta x. Oh, awesome. And that gives me my wave equation. My wave equation is thus utt is equal to t over mu u xx, or utt, oops, sorry. We can rewrite this, just one more. Utt is equal to c squared uxx, where c is the square root of the tension force and mass per unit length of the string.
Yo guys, what is subscribers, but I don't want you guys, thank you guys for over 150 subscribers, and obviously...
What is the meaning of theta with respect to string and reference? So theta is, in that snapshot you're looking at, theta is the angle that your string, the position of your string makes with the horizontal. That's just to force you to resolve your forces in T, because your forces might not necessarily be perfectly horizontal or perfectly vertical, right? But in the end, we realize that because theta is so small, it essentially disappears. So maybe let's put that comment here. What is C? C is square root of t over mu. If you take a look at the units, mass times acceleration divided by mass per unit length, I have units of mass times acceleration. I'm left with length per unit time. So C actually represents a velocity. Any questions about our derivation of the wave equation? So this is just to emphasize that this is correct. C is the velocity of the wave, yes. So last, let's just find our very easy initial conditions for our wave equation.
Hey guys, what's up? This is Vivek, and
we're not going to solve it, don't worry. What are the initial conditions of the wave equation, or what are the conditions for the wave equation? So first question, let's look at the wave equation. How many conditions do we expect? Second derivative with respect to t, second derivative with respect to x. So we need 2 time conditions, and we need 2 position conditions. Okay, the position conditions are obvious, that at the endpoints, they are fixed. So let's already write that down. Conditions. We 100% know the boundaries. The positions are 0 and pi. So u at any time t, 0 is equal to u at any time t, pi. They have to be fixed at 0. And the initial conditions, well, what are the initial conditions on the string? There is an initial flick of the string, which tells you what shape it's going to be. So let's assume that that shape takes on, so at time 0, it takes on an initial shape. Let's call that shape f of x. And what other initial condition can we have? Well, at time 0, can we assume that there's no velocity on the string? Yeah. Let's just assume that there's no velocity at time 0. So ut at time 0 at all other x is equal to 0 as well. So let's assume that this is one of our initial conditions. Is initial height of 0 valid? Yeah, for some points on the string, it might be 0, but not necessarily on all points. Yeah. Okay. So what are you going to show in the tutorial? So just to give you a taste, from your job is that we're going to give you the solution. All you need to do is check. The solution is given to us by 18th century French mathematician Jean-Laurent d'Alembert. So d'Alembert came up with this solution. He literally came up with this. His birthday is coming up. His birthday is November 16. He essentially like was just like playing around with examples, and he was like, oh shoot, this works. So his solution is UTX is equal to 1/2 f of x plus ct plus f of x minus ct. Your job is to check that this works. And we're going to do that in the next tutorial. Okay, so he's like, okay, let me play around with some examples. And he realized that, well, if I take f of x to be the initial shape of the string, move it forward by a velocity per unit time, backward by a certain velocity, and superimpose those two, take the average of those two waves, then that would be a solution to the wave equation. Okay? How do you check that it's a solution? Plug it into the equation, check the initial and boundary conditions. All right. Any questions? It works for any f of x. Ooh, there will be an f of x condition in the tutorial. But the issue here is you need an f of x that will allow you to be fixed at 0 and pi, right? Because of your initial condition or your requirement on the string. So what you're going to end up with is f of x has to be an odd function with period 2 pi. Okay. Guys, that's it for differential equations. Oh my god, we've come so far. And at the end, only 2 people remain. Thank you, the 2 people who are flicking the screen over here. Much appreciated. It's really made it much nicer for me to teach seeing people. It's quite hard when everybody else is hiding. What is that? Yeah. Oh, f of x is going to be a given function, a function that's given to you. Like in the same way that the function f of x was given in the heat equation, you're going to be given f of x. So right now we're using it to denote a general function f of x. Okay. Reminder, we have meet for tutorial on Wednesday. Then next week, Monday, is our tutorial. Okay, so that your Wednesday is free. Are you teaching 1508? I think so. I was gonna request to not teach it, but I think I don't have a choice, so I think I'm gonna, because they've been making me teach 1508 since it first started, and it's like, so this is the first semester that I'm not teaching 1508 again. So it's quite refreshing to do calculus. D hope over D time is always negative. It's negative because it's going up. No, it's not. Second derivative of hope with respect to time is. Turn on my camera when you remod for a different mod, not this one. For the heat and wave equations, we use c squared because we know that k has to be positive. Yes, correct. What did you study before this and where? What do y'all think I studied? So I was a student of literature, and yeah, now I teach math. No, just kidding. I did math as an undergrad. Yeah. Quite exciting. Oh, where? Oh, do you want to guess where? I think it's no. I mean, so I did my semester abroad at, oh, so sad. I hope you guys get a chance to go for semester abroad, like during your 4 years. Hopefully COVID disappears. I was actually in Boston for like a year. That was really nice. I was based at Harvard, and then I took a couple of MIT classes. So I really recommend, if you guys get a chance, you guys should go for time abroad. But it's a bit tough now with COVID. What other mathematicians' birthdays do you know? I know my birthday. No, just kidding. My birthday is coming up. That's why I canceled next week's. No, just kidding. No. Who's I feel I should know. I should know other mathematicians. No, I just know Jean-Laurent d'Alembert because he is always like we always teach him right like the week before his birthday. So like I always remember, oh yeah, it's his birthday coming. Oh, but guys, by the way, class is done. So there's still 50 people in the room. You're free to leave. This is it for today. Okay? How long have I been teaching? With NUS, I've been with NUS for 4 years.